Hello everyone, good evening. Voice is audible, right? Yes, I think voice is audible. Yes, okay, welcome. Good evening, good evening. Okay, so we're going to start freshly. So we're going to target UPSC 2025 mathematics optional, right? So it's been long time since I posted the last video. So first of all, sorry for that. Okay, so I'll try to complete linear algebra. I'll try to complete linear algebra in the next 20 days, right? So within the next 20 days, I'll try to complete linear algebra. And we'll also have test series gradually when we do linear algebra when we are doing linear algebra, right? um, Almost more than some 7 to 8 chapters I've already completed in YouTube, but it is not 100% I finished, right? I left over something. Okay, no problem. So we will start linear algebra very deeply, right? Let us start fresh. First of all, linear algebra comes in paper 1, right? So in paper 1, we have a linear algebra. Yes. Okay. So we'll start with the linear algebra, right? In paper 1, we have first chapter is linear algebra, right? So you know everything, right? Paper 1 carries 250 marks, paper 2 carries 250 marks. Um, Linear algebra will alone come for around 60 to 80 marks. You will have only from linear algebra, right? Very easiest topic. Easily you can score 60 to 80 marks only from linear algebra, right? You can easily attend all questions, right? They will ask only standard questions. They will ask only standard theorems, right? So just follow my notes. That is more than enough for you to attend any question on linear algebra, right? I will discuss more deeply. I'll make sure that you can solve any problem from linear algebra after watching these linear algebras upcoming videos, right? Okay, we'll start. uh, this is the syllabus of linear algebra, right? Paper 1, it comes under paper 1. So you can see we have already discussed about linear algebra syllabus, right? So linear algebra, so we have vector space over R and C, linear dependence and independence, subspaces, basis and dimension, linear transformation that consists of rank, nullity, and a matrix of linear transformation. And then we'll move on to matrix theory, right? Rank of a matrix, inverse of a matrix, and solution of system of linear equations, homogeneous and non-homogeneous system of linear equations, and then eigenvalues, eigenvectors, and Cayley-Hamilton theorem, right? So this is the syllabus of linear algebra, right? So very easy. So in this class, what I'm going to do is I'm going to introduce vector spaces, right? I'm going to introduce vector spaces. So to know vector spaces, we need the basic idea of group theory and field theory, right? So to know vector space, right? To understand vector space more deeply, we need the basic idea of group and we need the basic idea of field, right? So first, what I'll do is I'll go through the definition of group, right? Already I've discussed groups and fields in many of my videos, right? If you just go to modern algebra playlist, you can see almost 30 videos, right? But I don't want to introduce straight away what is vector space, right? To understand vector space, you need the idea of group and you need the idea of field, right? So first, what we'll do is I will define what is group, and then I'll give you many examples. I will define what is field. I'll give you examples. Then we will define vector space, right? So in this class, what we're going to do is, this is a flowchart of today's class, right? We're going to introduce what is group. I'm going to give examples of groups. I'm going to introduce what is field, and I'm going to give the examples of fields, and I'm going to introduce the definition of vector space, right? And then we will be seeing some examples of vector space, right? So definition of group example, definition of field, and then example, definition of vector space. We will be seeing 7 examples of vector space. After that, we will be proving 3 problems based on vector spaces, right? That is based on the definition of vector space. So this is what we're going to do today, right? So is it clear up to now? Yes, I think it is clear, right? Okay. So first we will start with the idea of group, right? First we'll start with the idea of group. See, I'm not going to deeply discuss about group theory, right? That is a separate, there is a separate paper called Modern Algebra where you will discuss group theory, ring theory, and field theory very deeply. Now I'm not going to discuss very deeply. I'm just going to give the definition of group example. That's it, right? When I'm covering that modern algebra, I will discuss more. As of now, I'm just going to touch up only, right? Group theory and field theory. Just the definition of group and a field. That's it. Okay. Yes. So first we'll define what is a group, right? First we'll define what is a group. Just a minute. Yes. First, what I'll do is I'll define what is group, right? So definition group, right? Yes, we'll define what is a group first, right? Okay. Okay. See, let us consider a non-empty set G, right? So we have a non-empty set G, a set that is not empty, right? So let G be a non-empty set. Let G be a non-empty set. Let G be a non-empty set, right? So we have a non-empty set G. Consider consider a binary operation. Consider a binary operation star, right? So let us call a binary operation as star. See, it can be anything. When I say binary operation, it can be addition, it can be multiplication, it can be composition. There are many binary operation, modulo operation, right? Yes. We will discuss that more deeply when we do modern algebra. As of now, we will stick more to addition and multiplication, right? Whenever I say operation, more or less we will stick on to addition and multiplication. So let G be a non-empty set. Consider a binary operation star on G, right? So we have a set G and then we have a binary operation star. So whenever I define a set G, you should also define a binary operation with that. What operation you are using in that set, right? Okay. Let G be a non-empty set. Consider a binary operation star on G. So denoted by G comma star, right? I have non-empty set G together with the binary operation star. Then G is said to form a group. G is said to be a group or G is said to form a group if the following conditions are satisfied. Right? I'm going to list out four conditions. If that conditions are satisfied by a non-empty set G together with the binary operation star, then we say that G forms a group. Right? Yes. The first condition is it should be closed. Right? It should be closed. Closure. Right? The first property that the non-empty set G should satisfy is called closure property. That is, you take any two element in G, right? You take any two element in G. See, we have a non-empty set G, right? You take any two element in G. For A comma B belongs to G, A star B also should be in G. See, suppose if your binary operation is plus, right? If your operation is plus, then you take any two element A comma B in G, then A plus B has to be in G, right? A plus B has to be in G. That is, sum of two elements should be in G. If your operation is plus, if your operation is multiplication, you take any two element in G, A into B, product has to be in G. If that is true for all A comma B, then that set is said to be closed, right? closure. Now, second property is associative. Associative. You take any three elements in G, right? For closure, you take any two elements in G, then A star B has to be in G. Star is the binary operation that we should define when we are defining set itself, right? And then we also define how to add and how to subtract. For associative, for you take any three elements in G. You take any three elements in G, A, comma B, comma C belongs to G. A star B star C is same as A, A star B star C. That is, I'm reordering the operation, right? A star B star C. That is, you perform B star C first, then you perform A with B star C. Here I'm performing A star B first, then I'm performing C. Both should be equal. Then we say that set G satisfies associative property with respect to that binary operation, right? And third is existence of identity. Existence of identity, right? Existence of identity. There exists an ID element, right? There exists an ID element. There exists an element E in G. There exists. There exists an element. There exists an element E in G. See, there should be some element E. E can be anything, right? I'm just denoting that to be E. It can be any element. But that element should satisfy there exists an element E in G such that when you operate A with that element, that is when you operate any element with that element in any order, it has to give me A again, right? There should exist an element E such that when you operate, you take any element, you operate with E, you should get back that same element. There exists an element E in G. When you operate E with any element, for all A belongs to G, you take any element, you operate with E, you have to get A again. If there exists an element like that, then that is called ID element with respect to that binary operation, right? Yes. And fourth is existence of inverse. Existence of inverse, right? For every A in G, for every A in G, you take any element. You should find some other element. There exists. If I write this means there exists, right? For every A in G, there exists an element A inverse that also in G. For any element A, there exists one more element, call that as A inverse. When you operate A and A inverse, such that when you operate A with A inverse, or when you operate A inverse with A, you have to get the ID element. You have to get the ID element. If that is true for all A, for every A in G, there exists an element A inverse, call that as A inverse. When you operate A with that, you have to get ID element. If that is true for all A belongs to G, then we say inverse exists for each element, right? Let G be a non-empty set. Consider a binary operation star on G denoted by G comma with respect to G comma denoted by G comma star. Then G is said to form a group if the G satisfies these four property, right? If G is said to form a group if these four conditions are satisfies, right? So we have a non-empty set G, and if it satisfies these four property, then we say that G forms a then we say that then we say that G comma star forms a group forms a group, right? I'm going to give many examples, right? Don't worry. So I'll extend this gradually. So we have a non-empty set G, right? You take any two element in G, A star B has to be in G, then we say it is closed. You take any three elements in G, A star B star C is same as A star B star C. There exists an ID, there exists an element E in G. E can be anything, right? But when you operate A with E, you have to get A again. ID element is unique. That will prove. ID element is unique. That will prove in modern algebra, right? And for every A, there exists one more element. Let us call that as A inverse. When you operate A with this element, you have to get ID element, right? Then we say if it satisfies these four conditions, then we say that G comma star forms a group, right? I'll also introduce the definition of abelian group. A group G is said to be an abelian group. See, first it has to be a group, right? So if it has to be a group, it has to satisfy these four conditions. A group G is said to be abelian if it satisfies commutative property. If it is satisfies sorry if it satisfies if it satisfies commutative property, that is A star B is equal to B star A for all A comma B belongs to G. A star B is equal to B star A for all A comma B. If a group G along with commutative property, a group G along with commutative property, that is if it satisfies five conditions, right? Four conditions for a group. If it satisfies one more condition also, that is if it is commutative, then we say that G is an abelian group. If it is not commutative, if it satisfies only these four conditions, we say a group along with this condition is said to be an abelian group, right? Okay. So we'll discuss examples, right? We'll discuss examples. Uh, let us consider, let G be a non-empty set. To check whether it's a group or not, we should have a non-empty set. We should have a binary operation, right? Yes or no? We should have a non-empty set. We should have a binary operation. Let us take the first example. Let us take a natural number with respect to addition. That is, my non-empty set is natural number. The operation I'm going to discuss now first is with respect to addition, and how to perform addition, usual addition which we will do, right? Usual natural numbers addition. Okay. Is it closed? Is it closed? What is the definition of closure? You take any two elements in G. What is our G here? G is natural number. You take any two elements in G. Here star is plus, right? That means if A and B are natural number, A plus B is also a natural number. Yes or no? So A plus B will also be in G. You take A to be 1. You take B to be 2. What is A star B? A star B here is A plus B. I'm discussing for usual addition subtraction, right? Usual addition and usual subtraction. Usual addition, usual subtraction, right? With respect to usual addition multiplication. That is what we're going to discuss now, right? That is, whenever you are adding A star B is A plus B, right? Here the addition is plus. And whenever you are multiplying, you need to multiply A into B. That is what usually we'll do, right? 2 into 3 is 6. This is usual addition, usual multiplication. Okay. Now consider natural number with respect to addition. Is it closed, right? Because you take any two natural number, the sum of natural number is again a natural number. So therefore it is closed, right? And for associative, again, I can add in any order, right? If A, B, C, you take A comma B comma C. A, B, C are natural number. So B plus C is natural. So A plus this number is same as natural number plus this number. Both will be same, right? Because natural number is commutative, right? So therefore it will be associative. It will be associative. Now, is there an ID element? You should find an ID element E such that you are for all A plus E has to be A, right? A plus E has to be equal to A. So usually let us consider this set, right? So A plus E has to be equal to A. That means E has to be 0, right? See, you give me one element 2, right? You give me element 2. What should be added to 2 to get 2 again? It is 0, right? So whenever my binary operation is addition, with respect to usual addition, right? Whenever my binary option is plus, with respect to usual addition, your ID element is always 0 because there exists an element E in G, A plus E has to be A. That means E has to be 0, right? There is no other element. You need to, if you have an element A, you should add one element to get A again. That element has to be 0, right? But 0 is not in natural number, right? But 0 is not in natural number, right? 0 does not belongs to G. So therefore, there is no ID element. Is it clear? For all A, there exists an element E such that you need to add A with E to get A again. Obviously, E has to be 0, but E 0 is not a natural number. Therefore, there is no ID element. For to be a group, it has satisfy 4 conditions. If one fails also, it is not a group, right? So therefore, it is not a group. Is there, see, already we seen it is not a group because there is no ID element. Existence of inverse, right? Since there is no ID element, obviously inverse will not exist, right? Because for all A, there exists A inverse such that when you operate A with A inverse, you have to get ID element. But ID element is not here, so we'll not discuss about inverse, right? We'll not discuss about inverse, but it is commutative, right? Because A plus B is same as B plus A. If A and B are natural number, it is not a group, so therefore obviously it is not abelian group also, right? Okay, group with commutative will be an abelian group, right? Group with commutative. Okay, now let us take natural number with respect to multiplication, right? The operation is multiplication. You take any two element in G, A comma B. A into B is also natural number, right? See, the operation is A star B. The star is the multiplication. You take AB in G, A into B. Product is also a natural number. Therefore, it is closed. Therefore, it is closed. Now, it is again associative, right? You can multiply in any order. Natural number is commutative also with respect to multiplication. You can multiply in any order, it will be equal only. Now, with respect to multiplication, under usual multiplication, your ID element always 1, right? Because A into something has to give me A again. So this has to be 1, right? A added with something, you have to get A. So that element has to be 0 if your operation is addition. If your operation is multiplication, A into something has to be A with respect to usual multiplication, right? That is very important. So this element has to be 1, right? This element has to be 1. So that means whenever your operation is multiplication with usual multiplication, that is A star B is A into B, then your ID element is always 1, right? See, remember the operation is very important. I'm stressing the word usual multiplication. I'm operating A star B as A into B. That is a usually will perform multiplication. In that case, only E is equal to 1. If my operation is different, E will change, right? If I multiply normally A into something A, under usual multiplication, ID element is always 1. Is 1 belongs to natural number? Yes, 1 belongs to natural number. So therefore, there exists an element 1 in G. When you operate, there exists an element 1 in G such that when you operate 1 with any element, you will get A again. Or when you operate A with 1, you will get A again. So therefore, 1 is your ID element and 1 belongs to natural number. Is it yes or no? See, you give me any natural number. I'm saying that my ID element is 1. You give me any natural number, give me 100. 100 into 1 will give me 100 only, right? There exists an element E. When you operate A with E, you will get A. So under multiplication, with usual multiplication, E element is 1. 1 is in natural number, so therefore inverse exists. Good, cool. Now existence of inverse. What is the definition of inverse with respect to multiplication? You give me any A, there exists one more element. When you multiply A with that element, you have to get ID element. What is an ID element? 1, right? So that means you give me any A, there exists one more element, so that A into this will have to give me ID element. And we know ID element is 1 with respect to multiplication under usual multiplication. So this element has to be 1 by A, right? You give me any A, you give me any number, 100. 100 into what is 1? That has to be 1 by 100. It has to be 1 by 100, right? 10 into what is 1? It has to be 1 by 10. So, the inverse of A is 1 by A. Yes or no? Under multiplication. Because A into something has to give me 1. That element has to be, A inverse has to be 1 by A. Is 1 by A is a natural number. See, you give me 2 belongs to G. But 1 by 2 doesn't belongs to G, right? Because 1 by 2 is natural number, not a natural number. It for every A, you should find A inverse such that A into A inverse has to give me 1. It is not true for all A. If you take A to be equal to 1, then it is true because 1 into 1 is 1. What happens if you take A to be equal to 5? Your inverse is 1 by 5. But 1 by 5 is not natural number. Yes or no? For every A, you should find one more element. A into that has to give me 1. So therefore, there is no inverse, right? There is no inverse. It is commutative, right? It is commutative. It is commutative because A into B is equal to B into A if A and B are natural number. So since there is no inverse, it will not be a group, and also it is not abelian group also. A group along with commutative property. It is not a group. Then only we can say an abelian group or not. So natural numbers with respect to addition as well as multiplication is not a group. Natural number with respect to addition, natural number with respect to addition and multiplication is not a group, right? So one is your ID element, but there is no inverse. Yes. Now we'll move on to integers. Integers with respect to addition. Integers with respect to addition. It is closed. You take any two integer, the sum is also an integer. 1 belongs to integer, 2 belongs to integer. What is 1 plus 2? 3, which is again integer. Sum of two integer is again integer. Okay. It is also associative, right? Obvious. Now there is an ID element, right? With respect to addition, what is your ID element I have said? E is equal to 0. So E is equal to 0 belongs to G. When you operate A with 0, it will be A again, or when you operate 0 with A, you will get A again. So therefore, E is equal to 0 is your ID element because 2 plus 0 is 2, 3 plus 0 is 2, and also 0 belongs to integers. So therefore, inverse, ID element exists. Now, existence of inverse. See, I have said that with respect to multiplication, inverse element has to be 1 by A. With respect to addition, A plus something has to give me ID element. ID element is 0, right? With respect to addition, your ID element is 0. A plus something has to be 0. So this element has to be minus A, right? This element has to be minus A, right? This element has to be minus A. And also minus A belongs to G here, right? Because if A is integer, minus A is also an integer. So give me 2. There exists minus 2. Such that 2 plus minus 2 is 0, which is your ID element. You give me any element. You give me minus 100. I can give you 100. Both my element are in G. And addition is adding will be give us resultant is 0, which is also an element of G. So therefore inverse exists, right? So A inverse is minus A. A inverse is minus A because A plus minus A is equal to ID element or minus A plus is equal to 0. So inverse also exists, right? So this also exists, this also exists. It is also commutative, right? Because A plus B is equal to B plus A if A and B are integers. So therefore, integers with respect to addition forms a group as well as it is abelian group also because a group along with commutative property is said to be an abelian group, right? Yes, great. Now we'll move on to integers with respect to multiplication. Integers with respect to multiplication. It is closed, right? Because you give me any two integer, the product is also an integer. So therefore, the product is also in G. It is associative. You give me, you take any three elements in G. G is our integer here. A star B star B is same as A star B star C. Now we know for multiplication E has to be equal to 1 is our ID element, and we know 1 belongs to G, so that A into 1 is same as A, 1 into A is same as A. So E is equal to 1 is the ID element and 1 belongs to G. Super. This is also great. Now with respect to multiplication, for A inverse is, what is for A inverse? It is 1 by A. Let us take 2 belongs to G. G here is integer. But 1 by 2 doesn't belongs to G, right? Because 1 by 2 is not an integer. 1 by 2 is not an integer, right? For every A, 1 by A has to be G. So if A is equal to 2, 1 by 2 is not belongs to integer. So therefore, for a inverse to exist for all element, I given you a counter example that for if you give me 2, inverse of 2 is 1 by 2 with respect to multiplication, but 1 by 2 doesn't belongs to G. See, the definition is for every A in G, there exists A inverse that should also be in G. You should not say that, sir, 1 by 2 is an ideal inverse. 1 by 2 has to be in G. 1 by 2 is not in G here. So therefore, it is not, inverse does not exist. So therefore, but it is commutative, right? So therefore, it is not a group as well as it is not abelian group because inverse does not exist. Okay. Now we'll move on to rational numbers with respect to addition and rational numbers with respect to multiplication. Rational numbers with respect to addition, rational numbers with respect to multiplication. Sum of two rational number is rational number. It also associative because you can change the order. It is always commutative with respect to addition. ID element E is equal to 0 is ID element with respect to addition under usual addition because A plus E, A plus 0 is equal to A and 0 plus A is equal to A. So E is equal to 0 is the ID element. When you add 0 with any element, you will get A again. E is equal to 0 is the ID element. Now, very important. You give me 2. What is the inverse of 2? 1 by 2. Is 1 by 2 a rational? 1 by 2 a rational? Yes. You give me 100. What is the inverse? 1 by 100. Is 1 by 100 a rational? Yes. Inverse exists for infinitely many elements, but except one element. You give me 0. What is the inverse of 0? 1 by 0. Is 1 by 0 belongs to G? See, for every A inverse has to be in G. For infinitely many elements, 1 by A is in G, but for only one element 0, the inverse of 0 is not in G. It has to be true for every A. For every A in G, there exists A inverse. Here you can see for infinitely many element A inverse exists. You give me 1 lakh, I can give you 1 by 1 lakh. You give me 2 crore, I can give you 1 by 2 crore. So that this into this will give you 1. But if you give me 0, I cannot give you inverse element. So therefore, inverse doesn't, for 0 there is no inverse. 0 belongs to G, but 1 by 0 doesn't belongs to G. So there is no inverse element. This is the only element that is troubling us. This is the only element that is troubling us. If I remove 0 from the set of rational numbers, then it will be a group, yes or no? If I remove 0 from rational numbers, then it will be a, for every element inverse exists. No, note it down. So therefore, inverse exists only for non-zero element. That is a core idea. Inverse exists only for non-zero element. So therefore, it is commutative. It is not a group, and also it is not abelian group. Okay. We are discussing for addition. Oh, okay. See, we'll just copy paste here, right? We are discussing for addition, but I have explained for multiplication. Okay. With respect to addition, inverse exists, right? For every A, minus A is also, for every A, minus A is also a rational, right? A inverse is minus A here, right? Because A plus minus A is 0, right? So therefore, inverse exists. With respect to addition, inverse is minus A, right? As of now, talked only for with respect to multiplication I have talked, right? Okay. With respect, it is commutative. It is group as well as it is abelian group. With respect to multiplication, it is closed. It is associative. E is equal to 1 belongs to G is the ID element, is the ID, but it is not closed, right? Sorry, it is there is no inverse. 0 belongs to G, but 1 by 0 doesn't belongs to G. There is no inverse, but it is commutative. So therefore, it is not a group, and also it is not a abelian group. Is it clear up to now? With respect to addition, it is a group only, right? Because for every a, minus a is a rational number. For 0, minus 0 is rational, right? Okay. Now we'll move on to real numbers. Real numbers with addition. It is closed. It is associative. E is equal to 0 is the ID element, and a inverse is minus a, and it is closed, so it forms a group, and also it's a abelian group, right? Because sum of two real number is real number, and then also has an associative property, and e is equal to 0 is the inverse element. When you add any element with 0, you'll get that element back again, and a inverse is minus a if your operation is addition. So therefore it is group, also it is commutative. Again, real number with respect to multiplication, it is closed, right? It is closed. It is associative. E is equal to 1 belongs to G is the ID element, because when you operate A with 1, you will get A again. And with respect to multiplication, again inverse exists for infinitely many elements, but again 0 belongs to real number, 0 belongs to G, but 1 by 0 doesn't belongs to G. No inverse. It is commutative. It is not a group. It is not a abelian group. Yes or no? Because 0 is the only element that is doubling S. Infinitely many element has inverse, but 0 doesn't have inverse. If I remove 0 from real number, and if I remove 0 from rationals, it will be a group with respect to multiplication also. Okay. Complex numbers with respect to addition, complex numbers with respect to multiplication. Sum of two complex number is complex number. It is associative. What is the ID element? 0 plus 0i is the ID element, right? 0 plus 0i. A plus b is a complex number. When you add, you give me any complex number a plus bi, you add 0 plus 0i, you will get a plus bi again. So this is the ID element. And minus a inverse is minus a minus bi. When you add, you give me 2 plus 3i, you add minus of 2 plus 3i. It will be a plus a inverse will give you 0, right? And also it is commutative. It is group as well as it is abelian group. Now complex numbers with multiplication, again the same here. 0 belongs to G, but 1 by 0 doesn't belongs to G. It is commutative, so inverse does not exist, not a group, not an abelian group. E is equal to 1 plus 0i is the ID element, because when you multiply 1 plus 0i with a plus bi, you will get a plus bi again. You will get a plus bi again. Now you can see that integers with respect to addition forms an abelian group. Rational numbers with respect to addition forms an abelian group. Real number with respect to addition forms an abelian group. But with respect to multiplication, none of them is a group. Yes or no? With respect to multiplication, none of them is a group. But note, R star, right? I'm going to give a new set called R star. R star means all real numbers except 0. All real numbers except 0, right? R star with respect to multiplication forms an abelian group. Yes or no? With respect to multiplication, we are not getting a group because of 0. For 0 element only, we are not getting 0. We are not getting inverse. So if I remove 0 from this set, then every element will have an inverse. Obviously, this will take a tick. So therefore, it will be abelian as well as it is. It is a group as well as abelian. And if I remove 0 from complex number, it will be an abelian group with respect to multiplication. Right? If I remove 0 from rationals, it will be a group with respect to multiplication. So R, and similarly C star, comma dot forms an abelian group. Real numbers doesn't form an abelian group, but R star forms an abelian group. That is, if I remove 0 from real number with respect to multiplication, it will be an abelian group. See, all these examples here are an examples of infinite group. Why I am saying infinite group? Because your set G is infinite, right? G comma star. Here G is natural number. Here G is integer. Here G is rational. Here G is real number. What about irrationals? Irrationals is not closed at all. Irrationals is not closed at all. Sum of two irrational number need not be irrational. Sum of two irrational need not be irrational. You take root 2 as one number. You take minus root 2 as other number. What is sum? It is 0. Is 0 and irrational? So it is first step itself, it is closed. Sorry, it is not closed. Closed means that is closed. Irrationals with respect to addition, not at all closed, because a plus b is not belongs to G. And similarly with respect to multiplication, product of two irrational need not be irrational. You take a to be root 2, b to be root 2 again. Root 2 into root 2 is 2. 2 is not irrational. So sum of two irrational need not irrational. Some product of two irrational need not be irrational. So if you take irrational number, it will get closed in the first state itself. It is not closed under addition as well as it is not closed under multiplication. So I'm not considering here. Right? All these are examples of infinite groups. Right? There is also many finite groups. There is also many finite groups. So examples of finite groups, I'll discuss this more briefly when we do modern algebra, right? Examples of finite group. Zn, right? Addition modulo n, right? Addition modulo n, addition modulo n, nth roots of unity, that is the solutions of z power n is equal to 1, forms a group. Cube roots of unity, the solutions are 1 omega omega square, that forms a group. It is also a finite group because it has only 3 elements. Solutions of z power 4 is equal to 1. The solutions are 1 minus 1 I minus I. It has only 4 elements, that forms a group. Right? These are examples of finite group. There are many groups as of now. Just remember that Zn under addition modulo n is a group, and also nth roots of unity are examples of finite group. Is the definition of group is clear up to now? See, real number is not a group with respect to multiplication. But if I remove 0 from real number, it is a group with respect to multiplication. Complex number is not a group with respect to multiplication. But if I remove 0 from complex number, it will be a group, because 0 is the only element that is doubling us in inverse part, right? Okay. Now, as of now, I have given you what is the definition of group, right? We have a set non-empty set G. If G satisfies 4 conditions, then we say it is a group. That's it, right? Okay. Now, I'll introduce the definition of field. Definition. Field. See, for group, you have a non-empty set G. You have only one binary operation. For a group G, you should use for to be a group, you should have a non-empty set. There should be only one binary operation defined on G. That can be plus or it can be multiplication as of now. Now for a field, I'm going to have two operations in one set. Right? I'm going to have two operations in one set. Let F be any non-empty set. Let F be any non-empty set. Let F be any non-empty set. Let us consider two binary operation. Let us consider two binary operation plus and dot on F. Right? I'm going to have a two binary operation in one single set. That is denoted by I'm going to have a set F with respect to two operations. I'm going to have addition as well as multiplication. Right? The two operations are addition as well as multiplication. Let F be a non-empty set. Let us consider two binary operation plus and dot on F denoted by F plus dot. Then F is said to be a field if the following conditions are satisfied. The set F with respect to plus is an abelian group, right? That is, you have a non-empty set F, right? I'm going to have two binary operation in this set, plus as well as multiplication. With respect to plus, it has to be an abelian group. That is, with respect to plus, it has to be closed, it has to be associative, there should exist an ID element, there exists inverse for all A, and it's also commutative with respect to plus. With respect to now F comma dot, that is with respect to the same set with respect to multiplication should satisfy should satisfy the following condition, right? The first is with respect to multiplication it should be closed. It should be closed. That is, you take any two element in F, then A into B should also be in G. With respect to multiplication, it should be closed. You should be associative also with respect to multiplication. That is, you take any three element in F, A into B into C is same as A into B into C. Existence of ID element. With respect to multiplication should have ID element. There exists an element E in G such that A into E is same as E into A is equal to A. With respect to usual multiplication, E is equal to 1. With respect to usual multiplication, E is equal to 1. Okay. Now, very, very important thing is existence of inverse non-zero element should have an inverse. Non-zero element should have an inverse. Very important. With respect to multiplication, non-zero element should have an inverse. Except 0, every element can have inverse. I'm giving a lenient for you, right? That is, for every x not equal to 0 belongs to G, there exists x inverse such that x into x inverse is equal to E, x inverse into x. That is, non-zero element should have an inverse, right? Okay. And also it is commutative under multiplication. If this happens, then we say it is a field. That's it, right? Now, can I say real number with respect to with real number is a field? Can I say real number is a field? Yes, right? Examples. Real number with respect to plus dot is a field. Yes or no? See, real number is not at all group with respect to multiplication because for 0 there is no inverse. But here for existence of inverses, only non-zero element should have an inverse. Every non-zero element should have an inverse. That is true for real number, right? For every non-zero element, it has inverse. So real number is a field. Similarly, complex number with respect to plus dot is a field. That's it. Integers is not a field, right? Non zero is a non-integer, non-zero integer, but 1 by 2 is not at all an integer. But if I consider real number and complex number, every non-zero element has an inverse with respect to multiplication. So therefore, R, real number is a field and complex number is also a field. Real number is not a group with respect to multiplication because 0 doesn't have inverse. But in field, non-zero element should have an inverse with respect to multiplication. We don't care about 0. Every non-zero element should have an inverse. That is true there. So therefore, real number is a field. Right? Yes. So field means you should have two binary operation. With respect to plus, it should be an abelian group. With respect to dot, it is same as saying abelian group with the only condition that see all these are with respect to multiplication same as saying abelian group. And the only thing is non-zero element should have an inverse. Except 0, every element should have an inverse with respect to multiplication. Can I simplify this to some more extent? If we say f is a field, with respect to plus, it has to be an abelian group. With respect to dot, it has to be an abelian group. But the only thing is, in abelian group, every element should have an inverse in the inverse part. But here, non-zero element should have an inverse. Except 0, every element should have an inverse. That is true for real number and complex number. Therefore, real number and complex numbers are field, right? Yes, so we are done with the basic definition of groups and fields. Now we'll move on to vector space, right? We are coming to the core part of definition of vector space. Yes, definition, vector space. Okay, let B be any non-empty set. Let B be any non-empty set. Let B be any non-empty set. Let F be any field. Let F be any field. See, usually in vector space, if I say F is a field, 99% it will be either real number or complex number. Let F be any field. There is also finite field also Zn, Zp that we will do in modern algebra. Let B be any non-empty set and let F be any field. We have two set now. Let B be any non-empty set, right? Let B is any non-empty set. B can be a non-empty set, and we have a field F, right? We have a field. Usually, this will be either real number or it will be a complex number, right? Because integer is not a field. The examples in real number and complex numbers usually will take that as field, right? So let B be any non-empty set, and we have a field. See, I cannot write this directly, right? You should know what is field. That is why only I have given you 1 hour to explain what is group and what is field. Okay. Let B be a non-empty set and F be any field. B is said to be B is said to be B is said to be a vector space over the field F, over the field F, denoted by B of F, right? Then B is said to be a vector space over the field F. Very, very important. Field plays a very important role. Whenever we say vector space, we should have a non-empty set, we should have a field. Then this B is said to be a vector space over this field. This field can be real or complex as of now. So B is said to be a vector space over the field F, V of F, if the following conditions are satisfied. First, this B, this B, this B with respect to plus has to be an abelian group. B with respect to plus has to be an abelian group. Can you understand why I stressed the importance of abelian and field, right? If I simply now it is easy for you to understand, right? This set has to be an abelian group with respect to addition. That means that it has to be closed associative, there should exist an ID element, and there should exist inverse, and it is commutative with respect to addition. If it is usual addition, your ID element is 0, your inverse is minus a. This B plus, this B plus is an abelian group. This B plus is an abelian group. See, for this condition, you have to prove 5 things. To prove B plus is abelian group, you need to explain, you need to understand, and you need to prove 5 things, right? Okay. Now, you take some element alpha and beta in field. You take some element u and b. Just for understanding, I'm writing ub and alpha beta. Alpha into u plus b is same as alpha u plus alpha b, right? That is, I'm distributing this, I'm joining these two, right? Field and vector. Alpha into u plus b is same as alpha u plus alpha b for u comma b is in b, alpha belongs to field. Third, alpha plus beta into u is same as alpha u plus beta u, where for alpha comma beta belongs to field, this u belongs to b, right? Fourth, alpha beta into u is same as alpha into beta u for alpha comma beta belongs to field, u belongs to b. Fifth, 1 into u is equal to u, where 1 is the unity of f. 1 is the unit element, right? Unity means ID element of 1, right? So if that B satisfies this 5 condition, then we say B is a vector space. B of f is a vector space over f. That's it. To be a vector space, we should have a non-empty set, we should have a field. This non-empty set has to be an abelian group with respect to addition. I'm joining these two. You take an element uv, you take an element alpha beta. Alpha into u plus b is same as alpha u plus alpha b. Alpha plus beta into u is same as alpha u plus beta u. Alpha beta u is same as alpha into beta u. 1 into u is equal to u. For 1 belongs to f, which is the ID element. So if it satisfies, so whenever you need to prove a vector space, you need to prove 5 things. But in first thing, you need to prove 5 things. You need to prove 5 things overall. But in proving one, you need to prove 5 things: closure, associative, existence of ID, inverse, and commutative. Is it clear? Yes. Now we're going to see 7 examples of vector space. Examples of vector space. See, all this can be asked in exam, right? Prove that this is a vector space. Prove that this is a vector space. I'll be giving 7 examples. All things are possible exam questions. Examples of vector space, right? Okay, the first example is the space Rn over any field is a vector space with usual addition and scalar multiplication. The space is a vector space with usual addition and scalar multiplication. See, Rn means n tuple, right? If n is equal to 1, then your V is, see, this means your V is n tuple, and your field can be anything. It can be, mainly here, it can be either real number or complex number. So you have, see, Rn, if n is equal to 1, you will have real number. So your V is real number. If n is equal to 2, you will have R2. R2 is set of all ordered pairs x comma y in two-dimensional plane. If n is 3, it will be R3. So your V is R3, which is set of all three tuples, three-dimensional space. So in general, it can be any n-dimensional space over a field F is always a vector space. With usual addition and scalar multiplication, usually how we will add real number? Usually how we will add two real number? You will add the corresponding parts, right? That is uh, x1, x2, x3 and so on up to xn plus y1, y2 and so on up to yn should be added as x1 plus okay with usual, let us say x1, x2 and so on up to xn with the first and y1, y2 and so on up to yn. How we will add corresponding tuples x1 plus x2 dot 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 x1 plus y1 comma x2 plus y2 and so on up to xn plus yn. And how will scalar multiply alpha times x1, alpha times x2 and so on up to alpha times xn. See, whenever you need to prove vector space, first of all you need to tell the scale. You got to tell the addition and scalar multiplication. How you are defining addition and how you are defining scalar multiplication. That is very very important, right? Whenever you are saying it is a vector space, under what operation is vector space? How you are adding the elements? How you are multiplying the elements? That is very important, right? Okay, so we will prove this. Okay, so what is your B? B consists of Rn. I'm generalizing this, right? If n is equal to 1, B is real number. If n is equal to 2, it is set of all ordered pairs. And your field can be anything, right? It can be any field. Now, what is our V here? Here, V is Rn, V of F. V is Rn and F is any field. And F is any field. So, we need to prove, what we need to prove? We need to prove Rn over any field is a vector space. Rn over any field is a vector space, right? So first we need to prove this B is an abelian group with respect to addition. Okay, so what is the first thing? First thing is B with respect to plus. So here B is Rn with respect to plus is an abelian group. We need to prove this, right? For proving this, we need to prove 5 things, right? We need to prove this B is an abelian group. That is the thing, right? We have here. This V has to be the abelian group with respect to addition, and then there are 5 things. For proving first thing, we need to prove 5 things. Okay, so first we will prove this. So we will have A. So it is closed. What is the definition of closed? You take any two element in G, then A plus B should be in G. Right? We are discussing only for addition. Now you take any two element in G. Let us take A to be. See, every element is a tuple here, right? Let us take A to be this, B to be another element, y1, y2 and so on up to yn. If it is two tuple means x1 comma x2 will be the element, right? One element will be a pair, x1 comma x2. So what is A plus B? What is A plus B? x1 plus y1, x2 plus y2 and so on up to xn plus yn. This belongs to G, right? Because this belongs to G, because sum of two real number is real number. This belongs to G. Every element belongs to G. So therefore whole element belongs to G. So therefore it is closed. Therefore it is closed. Now for associative, you take any three element A comma B comma C belongs to G. I need to prove A star B star C is same as A star B star C. See here every element is a tuple. Let us take A to be x1, x2, x3 and so on up to xn. Let us take B to be y1, y2, y3 and so on up to yn. Let us take C to be z1, z2, z3 and so on up to zn. Now what is A plus B plus C? What is A plus B plus C? A plus B plus C. What is B plus C? Y1 plus Z1, Y2 plus Z2 and so on up to Yn plus Zn. Now what is A plus this? A is x1, x2. So this will be x1 plus y1 plus z1, comma x2 plus y2 plus z2 and so on up to xn plus yn plus zn. Now what is A plus B plus C? Again it is same as this, right? Because we can shift the order inside x plus y plus z is same as y plus z plus x, that is same as anything. So we can always shift the order. So again it will be equal to x1 plus y1 plus z1, x2 plus y2 plus z2 and so on up to xn plus yn plus zn. So therefore it is associative. Existence of ID. There exists an element E. E is a zero tuple that is in G such that when you add any element x1, when you add any element x1, x2, when you add any element x1, x2 and so on xn with this zero element, you will get this element back again. Therefore, E is equal to 0, 0, 0 is your ID element. Existence of inverse. Existence of inverse for every A is an tuple, there exists minus A. So what is minus A? Minus x1, minus x2 and so on up to minus xn, such that A plus minus A will give you an ID element which is a zero tuple, right? So therefore inverse also exists and also it is commutative also, right? Because for A comma B belongs to G, so A and B are tuples x1, x2 and so on up to xn, y1, y2 and so on up to yn. A plus B is same as B plus A. So therefore we have shown that the set B is set of all n tuple Rn is a abelian group with respect to addition. So we are done with this first part, right? We are done with this first part. Now we need to prove these four things only. So V with respect to this is an abelian group. We are done with this. That is the first definition. Now second is alpha into U plus V is same as alpha U plus alpha V for alpha belongs to the field F, U comma V belongs to V. Now let us take U and V belongs to V and U is an element in V and every element is a tuple. Let us take U to be x1, x2, x3 and so on up to xn. Let us take V to be y1, y2, y3 and so on up to yn. Now what is alpha into U plus V? So alpha into what is U plus V? x1 plus y1, x2 plus y2 and so on up to xn plus yn. When you multiply alpha, it will be alpha times x1 plus y1, comma alpha times x2 plus y2 and so on, alpha times xn plus yn. This is alpha x1 comma Okay, can I write this element as okay alpha x1 plus alpha y1, comma alpha x2 plus alpha y2, comma alpha xn plus alpha yn. Can I write this as alpha x1, alpha x2, and so on up to alpha xn plus alpha y1, comma alpha y2, and so on up to alpha yn. Can I write like this? This is same as this, right? Alpha x1 plus alpha y1, alpha x2 plus alpha y2. Now, if I take alpha outside here, you will have x1, x2, and so on up to xn. If I take alpha again out here, you will have y1, y2, and so on up to yn. What is this? This is u. And what is this? This is v. So alpha into u plus v is same as alpha u plus alpha v, which is again true. Now third is alpha plus beta u is equal to alpha u plus beta u. This is what we need to prove. The third definition, third thing. Let us take u to be, u is a tuple, right? So x1, x2, and so on up to xn. So this will be alpha plus beta. This is scalar into x1, comma alpha plus beta into x2, and so on up to alpha plus beta into xn. Now, can I write this as alpha x1, alpha x2, and so on up to alpha xn plus beta x1, beta x2, and so on up to beta xn. Both are same, right? Alpha x1 plus beta x1. That is same as alpha plus beta x1. Alpha x2 plus beta y2. That is same as alpha plus beta x2. If I take alpha outside, you will have x1, x2, xn, which is same as u. If I take beta outside, you get u again. So alpha plus beta u is equal to alpha u plus beta u. Now fourth is alpha beta u is same as alpha into beta u. Again, this is obviously true, right? You take u to be, uh, let u to be equal to a tuple, right? Prove this, it will be true. Now 1 into u has to be equal to u. Now 1 into x1, x2, and so on up to xn is same as 1 into x1, 1 into x2, and so on up to 1 into xn, which is same as x1, x2, and so on up to xn, so which is same as u. So 1 into u is equal to u. So therefore, Rn over any field is a vector space. Is it clear? Rn over any field is a vector space. So to prove a vector space, they will say B of f. So you have to prove that set B is an abelian group with respect to addition, and you have to prove the next four things. Alpha into u plus b is alpha u plus alpha v. Alpha plus beta u is equal to alpha u plus beta u. Alpha beta u is equal to alpha times beta u, and 1 into u is equal to u. So therefore, Rn over a field f is a vector space, right? Okay. Example 2. Whenever I am saying vector space, you have to define how to add and how to scalar multiply. Set of all polynomials. Set of all polynomials over R is a vector space with usual addition and scalar multiplication of polynomials. You know how to add two polynomials, right? You add the corresponding like terms. So in that operation, it will be a vector space. See, here B is set of all polynomials. So that is over over a variable x. So a naught plus a1x plus a2x square. See, polynomial, there is no degrees mentioned. So it is a polynomial of, it will go on and on, right? There is no any finite degree. So it is a polynomial alone. Here, polynomial over R. That means here a naught, a1, a2 belongs to real number. You can always see this as a tuple, right? You can always see a polynomial as a tuple that consists, the tuple denotes the coefficient of constant x, x square, x cube, and so on. Is it yes or no? You can always visualize a polynomial as a tuple. That means you can always, since we already proved in the previous problem that set of all n tuples forms a vector space, and therefore polynomial you can always isomorphic to tuples, right? Because here a naught, a1, a2 are also belongs to real number, so it is always true, right? Okay. You know how to add two polynomials, right? With additional method defined as a naught plus a1x and so on, uh, a2x square plus b naught plus b1x plus b2x square. This is a naught plus b naught, a1 plus b1x, a2 plus b2x square, and so on. See, which is always isomorphic to adding the tuples, right? Adding the corresponding like terms isomorphic to tuples, right? Uh, and also this scalar addition, alpha times a naught plus a1x plus a2x square and so on is equal to alpha times a naught, alpha times a1x, and so on. This is how to define scalar multiplication. This is a vector space. So here you can see your V is set of all polynomials. V is set of all polynomials, and here F is your field. Now you need to show that V plus, I'm just going to tell orally, right? You can easily prove. First is set of all polynomials with respect to addition is an abelian group. Is an abelian group. Why? You take two polynomial, the sum of two polynomial is a polynomial. So therefore it is closed. See, if it is asked in the exam, you have to write, right? I'm not going to prove that. It will take so much of time. You can easily prove in your own. You take any two polynomial, the sum of two polynomial is again a polynomial. So therefore it is closed. You take any three polynomial. See, you can always see isomorphic to tuples. Whatever we did there, same you do here. You take any three polynomial, a plus b plus c is equal to a plus b plus c. And what is your ID element? Zero polynomial. 0 plus 0x plus 0x square plus 0x cube is your ID element. And for every polynomial a naught, for polynomial a naught plus a1x plus a2x square, the inverse is minus a naught minus a1x minus a2x square. That is your inverse, and also it is commutative also. So it will be an abelian group. Your ID element is 0 plus 0x plus 0x square and so on. Your inverse is minus a naught minus a1x minus a2x square and so on. When you add any polynomial, if you add that polynomial with this polynomial, you get zero element. And similarly, alpha into u plus v is same as alpha u plus alpha v, which you can again prove the similar thing. And alpha plus beta u is equal to alpha u plus beta u. And the fourth thing is alpha beta u is same as alpha into beta u, and 1 into u is equal to u, where u is the id element of f, sorry, unity of f. Unity is 1 for real number. Unity means with id element with respect to multiplication. So 1 is the unity. So 1 into this polynomial, again you will get polynomial again. So therefore p of p is a vector space. Now the extension of this, the subset of this. Third example is set of all polynomials of degree at most n. See, this is an, we are not talking about degree here. If I talk about degree, set of all polynomials of degree at most n is a vector space over R. That is, we denote by Pn of R. Set of all V is a set of all polynomials of degree n. You have to fix n. We need to fix n. If n is equal to 2, then set of all polynomials of degree at most n, less than or equal to n, right? Pn of R. Pn of R, set of all polynomials of degree at most n. Set of all polynomials of degree at most n is a vector space, right? Is set of all polynomials of degree exactly equal to n is a vector space. At most n means set of all polynomials of degree. So for example, what is P2 of R? P2 of R means set of all polynomials of degree. It can be constant, it can be linear, or it can be quadratic. I'm asking, is set of all polynomials of degree exactly n is a vector space? Need not be, right? For example, if I'm writing here at most, right? If I replace at most by exactly, suppose if I reframe the sentence like set of all polynomials of degree exactly n, let us fix n to be equal to 2. So let us take polynomial p of x to be x square. This is a polynomial of exactly degree 2. Let us take one more polynomial g of x, call that to be minus x square. So I have taken two elements in V. V is set of all polynomials of degree exactly 2. First itself it fails. First this V has to be an abelian group under addition. For that to be true, it has to satisfy 5 conditions. It is not at all closed, right? Sum of two polynomial, what is p plus d? What is sum of two polynomial? Is 0. Is this belongs to G? No, because what is the degree of this? It is not of degree 2, right? It is not of degree exactly 2. So therefore, set of all polynomials of degree at most means, you can see here the sum is 0. So it is of degree 1, sorry, degree 0, right? Constant term. If I reframe like at most, it will belongs to G. But if I reframe exactly, it will not be in G. So therefore, set of all polynomials of degree exactly equal to n is not a vector space. It is not at all a group with respect to V is not at all a group because it is not satisfy closure property. But set of all polynomials of degree at most n is a vector space over R. This is a subset of this, right? Pn of R is a subset of this P of R. Okay. Now example 4. Now example 4 is, let S be any non-empty set. Let S be any non-empty set and F be any field and F be any field. Consider B is the set of all functions, from S to F. Then V of F is a vector space. F is any field with usual addition and the scalar multiplication of functions, right? Usually how you will add and how you will scalar multiply. Okay, here V consists of all those functions. V consists of all those functions F from S to F. This F is all functions, this F is field. Then this is our V now. V over F is a vector space. So this consists of all functions. And you have a field. All functions will be here. It can be continuous, it can be discontinuous. It consists of all functions: sin x, cos x, e power x, 1 by x. V comma plus is an abelian group. Yes or no? It is closed because with respect to sum of two function is again a function. It is associative. It is again true. And what is your ID? F of x is equal to 0. 0 function is your ID function, right? Because when you add any with 0, you will get 0. 0 function is your ID function. And inverse is for every f of x in G minus f of x is also in G, that is your inverse. For example, you know, right? Okay, with respect to addition, sin x, what should be added to sin x to get 0? It is minus sin x. Minus sin is also a function. And also it is commutative. It is again true. And similarly, 2 alpha into u plus b is same as alpha u plus alpha v. Alpha plus beta u is equal to alpha u plus beta u. Alpha beta u is equal to alpha times beta u. 1 into u is equal to u, where 1 is the unity of f. Where 1 is the unity of f, right? Okay. Now fifth is, I'm going to consider a subset of this. Fifth is set of all continuous function. Here these consist of all functions. Consider only set of all consider only the set of all continuous functions, right? Here S consists of all those functions. You consider only continuous functions, right? Set of all continuous function defined on closed interval 0, 1. Uh, the set of all continuous functions, the set of all continuous functions defined on closed interval 0, 1 over real number, right? See, we will note this as denoted by set of all continuous function is 0, 1. C of closed interval 0, 1 is a vector space over M. See, here you consider field to be a real number here, right? You consider all those functions from F to real number. We talk about real valued functions. Now again, set of all continuous functions, right? This is a subset of this, right? Again, it's a vector space. Similarly, here your ID element is also a 0 function because 0 function is continuous function, right? F of x equal to 0 is continuous function. So again, if sin x is continuous, minus sin x is also continuous, right? So inverse again same. So fifth is set of all continuous functions defined on closed interval 0, 1 over real number denoted by C of 0, 1 is a vector space over real number. And the sixth is just a minute. Okay, fifth. Now sixth is you consider all m by n matrices. B to be, you consider B to be set of all m by n matrices, right? You consider B to be set of all m by n matrices, and you consider, you take any field. Sixth. Uh, the vector space, you consider all those m cross n matrices over a field, over a field. Here B is set of all m by n matrices, and the field is, it can be any real number, sorry, any field, real number or complex number. This will be a vector space, right? With usual addition and scalar multiplication, with usual scalar and with usual multiplication of matrix. This is a usually, you know how to add two matrix and how to scalar multiply a matrix, right? With that operation, it will be a vector space, right? Obviously, so here your V is, and I'll give you only very short proof. You can easily prove this. Here B is set of all m by n matrices, m rows, n columns. This we have to prove this B is abelian group with respect to addition. Obviously, right? You take two matrices, sum of two matrices again a matrix, so it is closed. Again associative, matrix addition is associative, and zero matrix is your ID element. Zero matrix is your ID element. And for inverse matrices, with respect to addition, is nothing but minus of that matrix, right? If A is x1, x2, x3, x4, for inverse is minus x1, minus x2, minus x3, minus x4. If you add that, will get zero matrix. And again, with respect to addition, it is commutative. So therefore, this is an abelian group with respect to addition. And again, alpha into u plus v is same as alpha u plus alpha v. That we can easily prove this. So therefore, b comma plus is an abelian group because it is closed, it is associative, and what is your ID element? ID element is nothing but zero matrix of order m cross n, and for every a, minus a is the, for every a in G, for a in G there exists minus a in G. So here a is a matrix, right? Such that a plus minus a will give you an zero matrix of order m cross n. And again it is commutative with respect to addition. So therefore this is abelian group with respect to addition, and alpha into u plus v is same as alpha u plus alpha v. Here u and v are m cross n matrices. This is always true. And alpha plus beta u is equal to alpha u plus beta u. Alpha beta u is equal to alpha into beta u. 1 into u is equal to u, where u 1 is the unity of f. Okay, the last example, a set of all convergent sequences. The set of all convergent sequences over a real number. Set of all convergent sequences over real number is a vector space. Set of all convergent sequences is a vector space, right? Here V is set of all convergent sequences, and F here is R, right? So you know what is convergent sequence, right? If you know real analysis, then you can connect with that. If not, just as of now, just note it down. Okay. So this is V is set of all convergent sequences, right? So this set is closed. You take two convergent sequences, sum of two convergent sequences again convergent. Uh, zero sequence. That is your ID element because zero is convergent. Yeah, easily you can prove this as a vector space. Now eighth is a last example. Consider V. Consider the set V. Consider the set V of all n cross n magic squares. Show that it is a vector space. Show that it is a vector space over R. Here V is set of all n cross n magic squares, right? You know what is magic square, right? The sum of rows, sum of columns, sum of diagonals, everything should be equal to the same. So V consists of all those magic squares. So V consists of all those n cross n magic squares. It is not that easy to create magic squares. We can easily create 2 cross 2 magic squares with easy examples, right? For example, let us take 2 element to be 2, 2, 2, 2. This is a magic square. Let us take V to be 4, 4, 4, 4. This is a magic square, right? Because every element at 2 plus 2 is 4, 2 plus 2 is 4, 2 plus 2 is 4. You add any element will be equal to 4. This is also a magic square. So V consists of all those magic squares here. So V consists of all those magic squares and F is a real number, field is a real number. Now you have to show this a vector space, which you can easily do this, right? So V comma plus is an abelian group. Why? You take two magic square, the sum of two magic square is again a magic square, right? For example, you take the two magic square. What is the sum of this usual addition, matrix addition? The sum is 6, 6, 6, 6, 6. This is again a magic square. So it is closed. And for associative, again you add three matrices in different order, you'll get the same magic square. If A, B, C are magic square, then A plus B plus C is same as A plus B plus C, which is again a magic square. And ID element is 0, 0, right? 0 matrix. See, I'm giving you only 2 cross 2 matrix. You can generalize for n cross n matrix. 0 matrix is your magic square also, right? 0 matrix is a magic square. Every element add up to 0. That is your ID element. And for every a, minus a is your you take 2, 2, 2, 2. Inverse is minus 2, minus 2, minus 2, minus 2. That is also a magic square, right? Every element will add up to minus 4. So inverse also exists. It is also commutative. So therefore this is an abelian group. What is your ID element? It is 0 square, 0 magic square. And similarly, alpha plus beta u is same as all. This is true, right? Because this will, here you are using matrix additional scalar multiplication here, so obviously it will be true. You have to prove this in exam, right? So whenever you need to prove vector space, you have to prove 5 things, and for first thing you need to prove 5 things. So overall you will be proving 9 things overall, right? Okay. So we'll move on to some problems, right? I'll do 3 problems and then I'll wind up the session, right? We're going to do 3 problems. With these 3 problems, we will be winding off this session, right? I'll give you 1 minute break. We'll continue after a 1 minute break. Okay, very important, right? Usually, all these 7 problems, uh, usually in all these 7 problems, we have used usual addition and the usual scalar multiplication, right? But here, the addition and the scalar multiplication are different. Usually, how we will add? See, here B is R2. Here B is R2. Here B is R2. That are all two tuples. And here F is real number. We know R2 of R is a vector space. R2 of R is a vector space with usual addition and scalar multiplication. That is how you will add two pairs. Correspondingly, you will add the elements. But if I redefine the addition as you whenever you take an element x1 y1 in V, you take another element x2 y2. Usually, how will add x1 plus x2, comma y1 plus I2, y1 plus y2. If I add like that, and usually how you will scalar multiply alpha times x1, alpha times y1. In that case, it is a vector space. We already proved. But if I define the operation as like this, did this operation is be a vector space over R? That is what they are asking. With the usual addition and scalar multiplication, this is a vector space. We know. We generally proved that Rn of R is a vector space. Rn over any field. Here n is 2. But if I redefine the operation like this, is this a vector space? I need to see. Right? Okay. We'll prove. First, P comma plus is an abelian group. We need to prove this, right? See, usually if they ask question like this means surely it will not be a vector space, 90%. If it is not a vector space, it is enough to give only counter examples. Very, very important. In mathematics, disproving is very easy than proving. To disprove, giving counter example is more than sufficient. Right? Giving counter examples. If you give counter example yourself, the invigilator will see that they will judge that you are talented. So is this a vector space? You give a counter example such that we need to show 9 things for vector space, right? First thing is abelian group. For that we have to show 5 things. Along with that, the fourth other things. So 9 overall we need to show. If at least one fails, it is not a vector space, right? Right? If at least one fails from that 9, at least one fails, it's not a vector space, right? Okay. So first we'll since the first problem, I will go one by one. First, we'll see whether it is closed or not. You take any two element. Let a comma b belongs to G. Here a is x1 y1, b is x2 y2. You can take any tuples, right? Now what is a plus b? X1 plus x2 comma 0. Very important. This is how you need to add. This belongs to G, right? See, here the second element is 0, no problem. That will be set of all. R2 consists of what? What is R2? This consists of all those x comma y such that x comma y belongs to real number. So if y is 0, x can vary anything. So this element will be in G. X1 plus x2 is a real number. So this is a real number. So real number comma 0 is an element of R2. So real number comma 0 will be in B. So AB, let us take a comma b belongs to B. Then a plus b is in G. Okay. So it is closed. Now for associative, it is again true, right? So let us take a comma b comma c belongs to B. Let us take a to be x1 comma y1, b to be x2 comma y2, c to be x3 comma y3. So you just check this, right? So a plus b plus c is same as a plus b plus c. What is a plus b? X1 plus x2 comma 0 plus c x3 comma y3. What is a? x1 comma y1. What is b plus c? x2 plus x3 comma 0. So when you add this, you will get x1 plus x2 plus x3 comma 0, x1 plus x2 plus x3 comma 0. So both are equal, right? So it is associative. This inverse sorry, is ID element exist? Is there an ID element? Is there an ID element? Let E1 comma E2 belongs to G be an ID element. Usually, what is the ID element in Rn of R? 0 tuple, 0, 0, 0. ID element is not there, right? Why? Because you take A belongs to B. What is A? A is a some tuple. Then x1, y1, when you operate with E1, E2, you have to get x1, y1 again. Yes or no? You take any element, you operate with E. Here E is an element of R2. You have to get x1, y1 again. What is this? x1 plus E1, comma 0. This is equal to x1 plus y1. They are not equal, right? They are not equal. See, x1 plus e1 comma 0. This is how you add these element, right? So therefore, you take any element. You take any element. For example, see, let us take 2 comma 4 belongs to B. Now with 2 comma 4, you need to add something. You have to get 2 comma 4 again. Not at all possible, right? Because the second element is always 0. That is what we are defining right here, right? Second element is always 0. Now here is, this is the sum of these two pair, which will never be equal to 2 comma 4, because here second element is 4. Here the second element is 4. So therefore, no ID. There is no ID element. Is it clear? Very, very important. Is it clear? Can you please comment on this? Is it clear? You take any pair, with that any pair you need to add to get that pair again. See, it is not true for all elements. If you take 2 comma 0, then it will be true. For 2 comma 0, there will be an inverse, right? But if you take an element like both are non-zero tuple, both are non-zero, in that case it is not possible. So no ID. So this itself fails. So it is not a vector space. Okay. So problem 2. And a field be real number. Okay. See here again, B is set of all, B is set of all R2, right? B is R2. B here is R2 and F here is field. We know R2 of R is a vector space with usual addition scalar multiplication. But here in the previous problem, the addition is defined like this and the scalar multiplication is defined like this, not a vector space. In this problem, the addition is usual addition. usual addition. But the scalar multiplication is you should not multiply this directly. Instead, you have to put modulus for this and then you have to multiply inside. Right? Now, first B with respect to plus is an abelian group. This is obviously true, right? Because this is a standard addition. In the Rn, in this we know how for standard addition this is a vector space, right? Because for standard addition it is closed, it is associative. 0 0 0 is the ID element, and for x1 y1 minus x1 minus y1 is your inverse. So V plus is an abelian group because we'll always use this condition here. We'll always use this to prove V plus is an abelian group, which is standard addition, which is always abelian group. Now we need to show the remaining four are true. But I'm going to give you a counter example now. Now, for to be a vector space, alpha plus beta u has to be equal to alpha u plus beta u. If I give you one, if I give one counter example, if I give you one counter example such that this condition fails, then it is not a vector space, right? It has to be true for all u belongs to be alpha beta belongs to f. It has to be true for all. Let us take alpha to be equal to 1, beta to be equal to 2. Let us take u to be some 1 comma 2. Just for understanding, I am taking this. Can we see whether these two are equal? Okay. Now what is LHS? What is LHS? Alpha plus beta u. Now what is alpha plus beta u? Minus 1 plus 2 into u. So which is 1 into u. 1 into what is u? 1 comma 2. What is 1 times 1 comma 2? Modulus of 1 into 1 comma modulus of 1 into 2. You should not multiply directly. You have to put modulus and then you have to multiply, which is same as 1 comma 2. Now we will find RHS. Alpha u plus beta u. What is alpha? Minus 1 into u. What is u? 1 comma 2. What is beta? 2 times 1 comma 2. What is minus 1 into 1 comma 2? Modulus of minus 1 into 1 comma modulus of minus 1 into 2. When you are multiplying alpha instead, you have to put modulus and then you have to multiply. Plus modulus of 2 into 1, modulus of 2 into 2. So which is 1 comma 2 plus 2 comma 4, right? Because modulus of 1 is 1, 1 into 1 is 1, modulus of 1 is again 1, 1 into 2 is 2. So 1 comma 2 plus 2 comma 4. This is usual addition. This is usual addition, which is 3 comma 6. They are not equal, right? They are not equal, right? Alpha plus beta u is not equal to. I have given you one counter example, that is more than enough. It has to be true for all alpha comma beta. I have given you one counter example such that alpha plus beta u is not equal to alpha u plus beta u if I define scalar multiplication like this. So it is not a vector space. See, mostly if they ask examine, in that case mostly it will fail some condition, right? Okay, last problem and then we're going to wind up the today's session. Problem 3. Let B be the set R2 and F be a field of real numbers. Examine whether B is a vector space over F with addition and scalar multiplication defined as addition is usual addition. scalar multiplication is 0 times alpha y. That is, when you multiply this, the first element will always be 0. Second element, we should multiply this alpha. Right? Okay. Now we need to prove is it a vector space or not. Examine solution. B with respect to plus an abelian group, right? Because is an abelian group. You don't need to prove this in exam. Because to show not a vector space, you only show which condition it fails. That is more than enough. So it is an abelian group. With respect to addition, this is a usual addition. This is always an abelian group. Now, for to be a vector space, 1 into u has to be equal to u, right? Where 1 is the unity of f and this u belongs to v, right? Now, what is unity of f? 1, which is again 1 is a unity of r. Now, what is 1 into x1 comma y1? Is this equal to 0 comma y1, which is not equal to u, right? 1 into u has to be u. So 1 into u belongs to v is r2. So let us take u to be some x1, y1. If you multiply with this, you have to get u again. But with this scalar multiplication, you will not get u because the first coordinate turns out to be 0. Right? Not true. So, not a vector space. That's it. Right? Because it last sum fails, alpha plus beta u is alpha u plus beta u. It fails this condition. Right? Yes. See, the addition and the scalar multiplication plays a very important role. These three problems are not vector space. If I redefine how to add and how to scalar multiply, all 7 problems are vector space with usual addition and usual scalar multiplication. But if I redefine, I element need not exist, some property may fail, that happens. So this is the core idea of vector space, right? So whenever I say vector space, you should have a set V, you should have a field F. This V has to be an abelian group with respect to addition. V and F combinedly as satisfy 4 condition. Alpha plus beta u is alpha u plus beta u. Alpha times u plus v is alpha u plus v. Alpha times u plus v is alpha u plus alpha v. Alpha beta u is alpha times beta u. 1 into u is equal to u. Right? In the starting of the class, we have defined what is group. We have seen examples. We have defined abelian group and we have defined field. And then to be a vector space, we should have a non-empty set V. We should have a field. This V has to be an abelian group with respect to addition. This V along with F should satisfy these 4 conditions. And then we have seen some examples with the usual addition and scalar multiplication. But if we redefine how we are adding and how we are scalar multiplying, some condition may fail. In that case, it need not be a vector space. Right. For the next class, we will introduce what is meant by subspace and then we will move on. Right. So thank you. All the best.